Come in. Join us right now. Okay, this is all the music I can give you. Many times, a conference like this would end with the presentation of a motivational speaker. But since we're trying to be smarter and more serious, we will have a presentation of a scientist. So get your minds ready and give a round of applause to Leah, straight from Armenia, from AMD. No. It's not good enough. Let's give a big round of applause, please.
Thank you. And thank you very much for all of you for being here on my topic of the hardware behind AI. So a few things about me. I am a FPGA design engineer working in AMD. I have started my career from the ASIC sphere, worked as a digital design engineer many years. And then it's already 3 years I've moved into a FPGA sphere. Let's start with the contest. Today we will talk about artificial intelligence embedded in the hardware devices. We will talk about AI chips, how they work, some examples of AI hardware, and bring some advantages and disadvantages that AGI have. And finally, we will talk about how to build a simple system for the AI. As I said, I'm talking today about hardware AIs. So here we will talk about AIs and all knowledge you need to up to speed for latest stage technologies. So artificial intelligence enclosing the whole world and conquer businesses and industries. So before talking AGIs, let's talk about hardware. Let's talk about artificial intelligence. I'm sure we all know what is artificial intelligence, but let me bring the concept of AI here more time. So artificial intelligence is a technique that enables machines and computers to simulate human behavior and problem-solving computations. So in field of computer science, AI encloses machine learning and deep learning. These disciplines involve the development of AI algorithms modeled after decision-making process of the human brain that can learn from available data and make them increasingly more efficient. So we will talk about artificial intelligence types. So let's define what is machine learning. Machine learning is a specialized form for artificial intelligence that focuses on development algorithms and statistical models that enables computers to make the prediction without any explicit interaction. So there is several models for machine learning: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So basically, machine learning model can be represented as a function that represents the computational or mathematical tasks and that refers the input to the desired output. So as a formula, it can be denoted as a function of x is equal to y, where input data x is a representation of learned future on which we can do a prediction. And the data must take the form of matrix, where each row corresponds to the example or observation, and each column represents to a example of abstraction of that example. Output label y represents the desired outcome that the machine learning model aims to achieve, and the f function is is a mathematical or computational task that refers to that map input X to output Y. It's a representation of mathematical calculation that dependencies between a desired outcome and the true label of the data. The specific form of F depends on the machine learning algorithms and the nature of task. For example, it can take a form of linear regression as described in functions. In decision trees, the function of F consists of series of decision rules that split the input space into regions corresponding to different output labels. And in linear networks, the function F involves multiple layers of interconnected nodes with activation function, allowing the model to capture complex nonlinear relationship. In this term, we can say that the model working in two phases, training or learning phase and prediction phase. During the training phase, the components of the model trying to adjust to the components, and the goal is to minimize the discrepancy between desired output and the true label of the input. During the prediction phase, the algorithm takes the trained model and make the prediction over there. So, what is the deep learning? Deep learning is a subset of machine learning that uses multi-layers, layer structure called neural network. So that to simulate the complex decision-making power of the human brain. A deep learning model basically based on neural network techniques and inspired by the human brain. It consists of multiple neurons or nodes in a layer structure that refers input to output. The layers between the input and output layers are called hidden layers, and the deep terms refers to the number of hidden layers. In neural network, the 100 can be the 100 or 1,000 hidden layers. There are three types of models using in deep learning: convolutional neural network, recurrent neural network, and transformer. CNNs convolves the future input and using 2D convolutional algorithm trying to process the task for 2D processes like images. CNN extract the data directly from the images. RNN is mostly worked in serial times and in sequential data. Transformer are try to track the dependencies between sequential data. So let's compare deep learning and machine learning. Deep learning is a specialized form of machine learning, and they are both the types of artificial intelligence field. Machine learning can offer various techniques, depends on the data you are processing, depend on the complexity of the problem you are trying to solve. Deep learning can achieve more higher accuracy, but it's the shortcoming of this is the complexity, and deep learning is requiring more data set to train, and thus it's taking the longer time to train. So deep learning, because it is complex, sometimes it uses as a black boxes, and these black boxes are trying to interrupt, to enclose the human behavior in terms of machines. AI chips can be vary across industries where high performance, efficiency, and computing is required, and they are improving customer service among many others benefits. For example, they used in data center. AI chips deployed in the data center to accelerate inference and training tasks. AI chips used in edge devices devices included in edge devices, such as smartphones, tablets, smart cameras, IoT devices, which brings high performance. Used in healthcare, in medical systems, in health devices, in diagnosis tool to diagnose diseases and treatment planning. Used in smart infrastructure such as smart cameras, smartphones, in automation vehicles, in agriculture, finance, retail, aviation. This list is not the end. There is many more areas where AI chips can find application. So the AI chips grow beyond different areas. And the benefits of using AI chips over traditional semiconductors include cost effectiveness, compatibility, flexibility, and established software ecosystem. Using AI chips in hardware can benefit in many areas. For example, from a competition point of view, generally all neural network training tasks converge to a coefficient classification that have a non-amount of multiplication. The specific CPUs use the specific multiplication process, which is called reduced precision format, for example, float 16 and careless multipliers. And using reduced precision format can allow many benefits from many areas. As I said, in compatibility, flexibility, also provide high bandwidth and low latency. So let's now talk about edge computing and edge devices. Edge computing is a distributed paradigm that brings computation and data storage closer to the device where it's been gathered. Compared to relying on a central location like cloud, edge computing allows real-time data to not suffer bandwidth and latency issue, which affect the application performance. To put in simpler terms, instead of running processes in cloud, edge computing runs the processes in local areas, such as computers, IoT devices, and this gives to proceed the process in a few milliseconds. AGI, it basically means running algorithm, AI algorithm on edge on devices using edge computing, where the AI algorithm is based on the data where the device in which the device has been gathered. The AI chips can represent can give many techniques to increase the speed. And here is I have bring the top-down view of generic AI chip and representation of these techniques. So the most important improvement of AI chips is parallel processing. Parallel processing can separate it into parts, data parallelism and model parallelism. Data parallelism split the input data set into different batches, such that each batch process sequentially, and each batch split across the different AI units or different chips connected in parallel. Model parallelism split the model into different parts, and each part is running on the on the same unit of the AI chip. So another one is low precision computing, which is sacrificing accuracy to gain the speed and efficiency. And here in the table presented the table, X-bit processor table in low precision format for each bit type. Memory optimization, another point is if AI algorithm memory access patterns predictable, then AI chips can optimize memory amount and location. On-chip AI provide more efficiency. There is some AI chips that have enough sufficient memory to store all AI algorithms inside the chip. This can be beneficial from compared to off-chip device memory. Another one in domain-specific languages. These are the languages that specific language for the specific chips. in contrast of programming languages that engineers write the code in human understandable language and then compiler translate it to the executable version. DCL is the specific language that can be understandable only for the specific chips. And one point is quantization is the technique that reduce the model type. For example, from high precision format, we can bring it to low precision formats such as integer or floating 16 or 32. So now let's talk about different types of AI units. The first one is a central processor unit, which is a hardware component of AI chips that can do mathematical and computational to solve these problems. So the smart devices in computer transfer the data, input digital signal, and then make the prediction on that device and computation on that data. And CPU is the key component that can handle these all tasks. It takes several phases. Fetching, it fetches the instruction from the memory, decode what the instruction really is, execute the instruction, and finally retire and store the information. Generally, all CPUs consist of ALU, processor registers, and control units. Arithmetic logic unit is possible to do arithmetical and logical calculation. Register provide the operands to the ALU and then save the operation of that ALU. And control unit is the part that doing the execution. The next one, the CPUs can be used in work in parallel, but mostly GPUs are associated with the parallelism because GPUs are specifically designed for parallel processing with thousands of similar, more efficient cores compared to CPUs. In high level, GPUs consist of many SMID multiprocessors, and in each given clock cycle, each processor of multiprocessor can do the different tasks, but with the same data input. The threads in GPUs are different than in threads in CPUs. Each microprocessor in GPUs has thread groups, and each thread within thread group sharing the competition resources such as registers and multiprocessors. Another types of AI hardware is tensor processor unit. TPUs are custom designed chips specifically optimized for accelerating AI workload, particularly deep learning, inference, and training tasks. TPUs can provide some advantages over hardware. They are excel at matrix processing. They are working in parallel. They support reduced precision format. They also memory hierarchy have a hierarchy optimization. They have a data flow architecture. They are power efficiency. They can consume less power compared to GPUs. And they have a scalability. Another one for hardware AI is FPGAs. FPGAs is a reconfigurable digital logic that connects a set of programmable logic blocks and configurable interconnection hierarchy. FPGAs is not a fixed function processor. A hardware description language, HDL, is used to configure FPGAs, and unlike the traditional CPUs, they are truly parallel. And here are several ways FPGAs are used. They are accelerating interface, customization, low power consumption, real-time processing, prototyping, high parallelism, and hybrid architecture. Now let's talk about interconnecting of different types of chips, units. Combining multiple CPUs with networking technologies such as Ethernet, InfiniBand, and custom clustering can create powerful distributed computing system capable of handling large-scale computation task efficiency. One method is Internet, which is a widely used technique to connect different CPUs with LAN and provide the high-speed interaction between CPUs. Another technique is InfiniBand, which are using in high-speed for providing high-speed connection, which are used in HPC and large-scale devices. The last technique is clustering. The CPUs are clustered and make a connection between this clustering. So now let's talk about interconnecting of GPUs. Interconnecting multiple GPUs involves creating a network technologies that enables communication and collaboration between between multiple GPU nodes in distributed computing environment. One technique used here is direct communication. Some GPUs can configure such way that they provide direct connection each other using SLI or NVLink, which are the techniques that are linking the GPUs together. One is PCI switches, which are using high-speed data transfer by connecting GPUs through PCI buses. High-speed networking techniques also used in GPUs. And another one is custom interconnects. There are some protocols and fabrics. There are and other devices which can connect GPUs. So interconnecting TPUs also have several points. The one is TPU pods. TPU pods is using to connect the data transfer, training data between TPUs using TPU nodes. High-speed networking also used here, and another option is custom interconnects, which include cloud TPU pods and transfer distributed training, which are specifically designed and working for Google. And for interconnecting FPGAs, there are several other types of connection. Custom interconnect fabrics means that there are some fabrics inside the FPGAs that can connect different FPGAs together. PCI are peripheral component interconnect express that connect PCI to the core unit to CPU. High-speed networking also used here, and another one, FPGA to FPGA connection protocols that allows different FPGAs to connect directly each other without connecting of CPU core. And heterogeneous computing platforms enables FPGAs to connect another units such as GPUs or CPUs. And another one is partitioning FPGAs in clusters and connect this cluster together inside the system. So here I have bring one example which run 4x4 multipliers and 16x16 multipliers. I have designed and implemented this with two types, with register-based and LUT-based. The process was running on 500 megahertz, and I have calculated propagation delays for each of type and the logic delay and net delay. As we can see from the result, propagation delays for LUT-based structure is less than in register-based, and with some constraints was designed 16x16 multipliers, and here we also can see that propagation delays on LUT-based designs are less, and we can conclude that R is higher the bit of multipliers, then we can gain from the speed based on LUT design. The main differentiation between traditional hardware and AI chips consists how much data it can store and process, and how the speed of processing the computation. There are some keywords which AI hardware differs from regular hardware. They are task-specific optimization, parallel processing, memory bandwidth, low precision computation, hardware architecture, and as we said already, power efficiency. Now let's talk about some things that AI hardware can't do. While AI hardware brings numerous advantages, there are also certain disadvantages to consider. Here are some potential drawbacks that AI hardware have. So the cost, because the AI chips are designed specifically for the specific task, so that means that the cost will be higher. Another one is rapid technologies advantages, because the industry are growing so rapid, and we need to run under it and produce AI chips regularly and very rapid. So another one is capability and integration challenges, limited flexibility and generalization, energy consumption, learning curves and expertise, and ethical consideration. And here are some areas that AI hardware has limitation. One is creative and abstract thinking. Because it is the machine, so it can be creative such a human brain. Common sense reasoning, ethical and moral decision making. The ethic is we can only to learn the machine how it should be behave, but it itself can't do the ethical thinking. Emotional intelligence is a human main point that the machine can't interpret it, and adaptability and learning flexibility. And let's discuss what is required to build an AI system. To building an AI system involves creating a coherent and functional interaction for working variant architectures for defining the tasks that can traditionally requiring human decision making. And here are some steps that are required to define AI system. First one is define a goal. Before writing your first line of code, you need to decide what problem you need to tackle. Firstly, we need to decide what problem and challenges the AI system needs to achieve, and then specify the objectives that AI system needs to address. Then we need to consider the market and changes and do the appropriate changes and based on the feedback of the market. Another one is gather and estimation the data. Data gathering and estimation is a critical phase in building AI system, as the quality and relevance of the data directly impact the performance and effectiveness of the AI model. So it is involved both gathering the data from different sources and estimate the missing points of the data. It includes the following stages: data gathering, data estimation, data validation, and data integration. Next one is implement the algorithm. Implementing the algorithm in AI build system involves selecting, designing, and coding the algorithms or models that will be used to analyze data, make prediction, or perform other tasks relevant to the AI system objectives. Before choosing the right algorithm, we need to design architecture based on that algorithm, and then implement the algorithm using the appropriate programming language or libraries suitable for that AI system. This process included several stages: algorithm selection, algorithm design, coding the algorithm, and testing using the validation, also cross-validation technique, and finally document the process of implementation the algorithm. The algorithm needs to learn. That was we call training. The most of scientists use the 18% of data to set data to train, and remaining 20% to use the input data. And here are some the steps that requiring to training the algorithms. The next one is deploy the final product. In the final stage, we are creating the user interface in its scope. And if it's a service, we build a brand over it. And in this stage, we need to adapt changes to find a marketplace and do the relevant changes over time. And if we succeeded, we can find a place in the business. So by following the mentioned steps, we can create the successful AI system, and it can find its place in the market. So it is the final slide, and thank you everyone, and I am here to answer your question, if any.
Thank you very much. Please raise your hands. All right, 3 hands, good. Once again, yes, thank you.
Thank you very much for presentation. Unfortunately, I cannot ask a question about all this FPGA design and all these things. It's not my area of expertise. But maybe I ask like standard question: how AMD sees the future of AI training and inference? Will it be based on GPU or TPU, or maybe some new technology? I don't know.
AMD basically specialized in GPUs. If you think in the terms of TPUs, it is producing GPUs for AI, and also some FPGAs used in AI, because beside of fabrics and RAMs, the current family of FPGAs included have some AI part and can perform AI tasks on FPGAs.
And by specialization of FPGA, do you mean that this is kind of FPGA specific for type of models like LLM, or what kind of specialization for FPGA?
Sorry?
I mean, based on GPU or TPU, you can work with multiple types of model. Mm-hmm. As for FPGA, is it FPGA specific for a specific type of model, like LLM model, or maybe image generation, or something like that?
Basically, the AMD is producing GPUs for AI, AI part, if I understand your question, right?
Okay, thank you.
I have a question. Is there a slide with a QR code?
Yeah, sorry. Mm-hmm.
Yes. Whoever's not engaged in the Q&A session, please scan and give feedback. Also, I need to inform you that in 15 minutes we will have the closing ceremony and the final prize giving gig with our partner. So more questions now, please.
Thank you very much for a very interesting talk. I have a question not about hardware. Do AI chips have hardware support for 3 laws of robotics? Are we safe here with AI chips?
For what robotics?
3 laws of robotics.
Three
laws. Asimov's one.
Can you name the 3 laws of robotics?
Something like toe shall not kill human.
The microphone.
Sorry. Robot should never kill human. Robot should be proactive to avoid human suffering. And I don't remember.
And we should make a lot of money.
Yeah. That's number 1.
There are several jobs that AI still can't handle. I think it will be in the scope of ethics and emotional thinking. Yes, your question will be in that scope. And currently, AI chips can't handle that. But in the future, maybe we can. The scientists can train the AI chips to handle also that task.
Sounds good. Thank you very much.
Thank you.
Thank you. On the last row. Right, we'll get to you.
Hi, thank you for the speech. So I wanted to understand better, as an AI developer who develops and trains and deploys model, how to choose the right hardware for each architecture or the right setup.
Yeah. So basically, as I said, CPUs can't work in parallel, and for parallel processing, if we require higher speed, we are choosing GPUs because they are the one that can work in parallel and give the high speed. For low efficient power consumption, we can use TPUs or FPGAs. FPGAs are less common than TPUs because they can solve the specific tasks, and TPUs are preferable in that sphere. And if we are going to create small systems, then FPGAs are the appropriate for that.
If I can do another question. For GPUs, there are a lot of libraries, and most frameworks have everything that is required to use them ready for AI. What about FPGAs, for example? Can I find everything that I need, or will I have to eventually code the hardware as well?
You can find for FPGAs, and you can run your AI algorithm on FPGAs based on your tasks which you are going to run. But there are, it's the specific on the tasks, so it is very difficult to say which type you can use. It is very specific, and you need to consider all the tasks, all the features, and then choose the appropriate units which can implement your task.
Thank you.
Thank you. Yeah, there, please.
Hello, thank you for your presentation. I would like to ask that from one of the slides related to performance, you have the line, the performance maintenance is one of the points. As I understood, you're mostly focusing on the FPGA. Could you provide a bit more information about the maintenance? Because as I know, the AMD not so long time announced a new generation of the CPUs, and as a result, it's a quite hot. And of course, for our data centers, we need to use the more liquid, the cooling stuff. And for FPGA, will it be a little bit cooled down or something like that? It would be nice if you provide some specific laboratory specification around that. And also, how do you make some measure of the performance of that changing this from single floating to int? In one of your slides, it shows.
From the point of FPGAs, FPGAs now have some AI part on that, and they can precede this calculation. Is it?
Just roughly the temperature and other stuff, because let's imagine I'm the engineer. For example, as a company, I bought for a lot of the FPGAs, and then I need to use the cooling. Maybe do I need to change? Do I need to how to prepare everything, all the environment for maintenance, for supporting? How is it going to be for the future? Did you already prepare it, everything, or not yet?
Everything is prepared for FPGAs if mean of power consumption, because as I said...
Just roughly, the numbers, comparing with some of the latest generation of the CPU or GPUs, if it will be nice.
I can't say the numbers,
Okay.
yeah.
Okay, good, thank you.
Thank you.